Today we're going to do something pretty interesting. We're going to take a look at the human heart, something we all have, something we all think we know, and we are going to completely reimagine it. We're going to put on our engineering hats and see how one of biology's greatest inventions gets translated into the world of data, code, and AI. So let's jump right in.
This is it. This is the big question for today. And yeah, it might sound like something straight out of science fiction, but I promise you it's happening as we speak. We're going to break down that incredible journey from the physical, thumping biological process of your heart beating into signals, images, and pure data that a computer can actually read, understand, and analyze.
All right, so to even get started, we have to do something kind of radical. We have to completely shift our perspective. For just a minute, I want you to forget everything you know about anatomy and physiology. We're not looking at the heart like biologists today. We're going to look at it like engineers. Okay, so what you see here are two totally different ways of looking at the exact same thing. On the left, you've got the view we're all used to, right? The biological one, it's complex, it's alive, it's intricate. But look at the right. That's the engineering model. It simplifies the heart down to its most basic functions. It's a pump, it's got pipes, it's got valves to control the flow. And this mechanical viewpoint, this is the absolutely essential first step in our journey from biology to data. So let's break that down even further. Here's the whole system laid out. You've got the pump, which is the heart itself generating flow. You've got valves, which are, just that, valves, making sure blood only goes one way. The blood vessels, those are the conduits, the pipes. And the body even has its own built-in sensors to monitor pressure and a controller to regulate the whole operation. And of course, a power supply providing constant energy. It's actually an incredible piece of machinery when you think about it that way. Okay, so if the heart is a pump, then it stands to reason that the massive network of our arteries and veins, well, that's the plumbing. And just like the plumbing in any house, sometimes things can go wrong. And this quote from our source material it hits the nail on the head. It's such a powerful and simple analogy. Think about the water system in a huge skyscraper. To get water all the way to the top floor, you're going to need a powerful motor. That's our heart. And you need a whole network of pipes to carry that water everywhere. And those are our blood vessels. And what's the number one problem in any plumbing system? A clog, right? A blockage. In our bodies, this is called an occlusion. And it's a really simple concept with, potentially very serious consequences. And a problem like that, well, it demands an engineering solution. So if you've got a blocked pipe, what's the fix? You've got to find a way to get it open again and then prop it open so it stays that way. In the world of bioengineering, one of the most brilliant solutions for this exact problem is the stent. At its core, a stent is basically a tiny scaffold. It's this small, expandable mesh tube that a doctor can guide right into a blocked artery. And once it's in place, it expands, it pushes all that blockage out of the way, and then it acts like an internal support beam, just holding that vital pipe open so blood can get through freely again. But don't let its tiny size fool you. Creating a modern stent is a massive engineering challenge. First, you have to design the perfect scaffold structure. Then you have to pick materials that the body won't reject. They have to be biocompatible. Many stents today even have a special medicated coating that helps prevent the artery from getting clogged up all over again. And on top of all of that, you have to engineer a really sophisticated delivery system, usually a tiny balloon on a catheter, to get this thing to the exact right spot and deploy it perfectly. It's amazing stuff. Okay, so we've seen the heart as a machine. We've seen a physical engineering fix, like a stent. But to really get ahead of problems, to diagnose them before they become severe, we need to take one more giant leap. And this, right here, is the most crucial part of our story today, the translation. How do we take all this physical action, the pumping, the pipes, the flow, and turn it into a language that a computer can actually understand? The bridge, the missing link between the physical, biological world and the digital world of computers, is mathematics. Engineers use these really complex equations and concepts like hemodynamics, which is really just a fancy way of talking about the physics of how blood flows, and they use electrical circuit analogies to create mathematical models of the entire system. This is how the translation happens. And this slide gives you a little peek into what that looks like. It's called a circuit model. You can think of it like a weather map for your circulatory system. You know how meteorologists use symbols for high and low pressure? Well, engineers can use electrical symbols to represent things like blood pressure, volume, and resistance to flow. It's a way of creating a digital blueprint, a functional twin of your heart and blood vessels that exist entirely as data. And what's the end result of these blueprints? Data. The rhythmic pulse of your blood, the pressure on your artery walls, all of those real physical forces get transformed into clean, predictable data curves and electrical signals. We have successfully translated biology into the native language of computers. So now that we can speak the language, we can do something truly incredible with it. We can feed all of this data to an artificial intelligence. And this is where the real power of this entire engineering approach gets unlocked: digital diagnosis. So the AI gets trained by feeding it just enormous amounts of this cardiovascular data. It learns to read the electrical signals from an ECG to spot arrhythmias. It learns to analyze every single pixel of an MRI or a CT scan. It scrutinizes the precise shapes of those data curves that represent blood flow. It basically learns what normal looks like, down to the tiniest, most subtle detail.
And right here, you can see exactly what that AI is looking for. A healthy heart produces a strong, clean, predictable data curve. But if there's a problem, maybe a weak valve or a small blockage, that curve is going to look different. It might be smaller, or a little flatter, or just irregular. And these are the subtle patterns that a human eye might easily miss, but an AI, it can spot them in an instant. At the end of the day, that's AI's superpower here: pattern recognition. By analyzing all these signals and data curves, it can flag potential problems, helping doctors make diagnoses with more speed and more accuracy than ever before. This is the real revolution. It opens the door to predicting problems before they happen and creating truly personalized treatments. It's a shift from reactive to proactive medicine. And that kind of leaves us with one last big thought to chew on. We started this journey by seeing the heart as just a simple pump, and we ended with an AI that can help diagnose it. This process, this idea of translating our incredibly complex biology into the clear language of data, is one of the most powerful tools we have in modern medicine. And it really makes you wonder, what other parts of the human machine are we going to re-engineer next?